So we finish up section 4.3, which is on the fundamental theorem of calculus part 2, by talking about some special properties of integrals that have this property of symmetry, and also talking about the area between two curves. So in the last video, we had computed the definite integral of the function sine of x between 0 and pi. So we were just sort of looking at the area between the curve and the x-axis here. And we had found that this definite integral was 2. But this time, what if we wanted to find the definite integral of sine of x dx? Not just from 0 to pi, but from negative pi to pi. Right, what if we also wanted to include this area right here? Okay, well, we could actually do this if we wanted to. It really just involves taking the antiderivative of sine of x, which would be negative cosine of x, and then evaluating it at the endpoints at x equals pi and at x equals negative pi, and subtracting it. So this would end up being negative cosine of pi minus negative cosine of negative pi. All right, and we could do kind of the same thing here, but negative cosine of pi is going to end up being the opposite of negative 1, because cosine of pi is negative 1, minus negative cosine of negative pi. Pi and negative pi are the same angle, or have the same angle on the unit circle, and so this is also going to be a negative 1 here. When all these ones, or once you start dealing with all these negative signs here, a negative, and a negative, overall this is just positive 1 minus 1. It's just 0. And that makes perfect sense because we're dealing with signed area here, and this function's perfectly symmetric. So this section that we see here, it's really the exact same section that we see here, just rotated around the origin. Right? Remember, an origin rotation is basically like a 180-degree rotation. So if we took this and rotated it all the way around, it's really the same shape here. And we also have to remember that this is signed area, so all of this represents positive area, and all of this down here represents negative area. So this is like an area of positive 2, this is an area of negative 2, and of course it's just going to cancel itself out. We call a function like this that has this property of having sort of perfect 180-degree rotation symmetry or origin symmetry. We call that an odd function. Not odd as in strange, but odd as in even or odd. And we call it that because we have functions like x cubed are also odd, right? X cubed looks like this, or x to the 5th power, which also looks something like this. Those are all odd functions, any x to an odd power. So this sort of has this nice property where as long as you're going from the same x value on either side, so for example negative pi to pi, or if we were going from negative 2 pi to 2 pi, or even if we were going from negative 100 to 100, if it's the same absolute value going from negative 1 to the positive 1, that area is always just going to cancel each other out, and you'll end up with an integral of 0. So we have this nice theorem which says if f of x is an odd function, so if f of negative x is equal to negative f of x, which really just means it's symmetric around the origin, just like this graph here that I kind of made up. You could rotate this around the origin and it would look the same. Well, then the area under the curve between negative a and positive a, the negative area below the curve and the positive area above the curve will cancel each other out, and you'll end up with an integral of 0. Now what happens if your function is something like cosine of x, which still has symmetry, but it doesn't have that rotational symmetry? This instead has reflectional symmetry, right? This is your y-axis. This is perfect rotation across the y-axis, right? Reflected across the y-axis. So what if we wanted to find the definite integral, let's say from negative pi over 2 to pi over 2 of the function cosine of x dx? Right? That's this area right here. Well, it's not going to be 0, right? Of course it's not going to be 0. All this area is above the x-axis. It's all positive. So it's going to be something positive. But the nice thing to notice here is that the area that you get over here on the left-hand side is going to be the same as the area that you get over here on the right-hand side, right? And so what we can say is that this is going to be the same as the definite integral from 0 to pi over 2 of cosine of x dx, but multiplied by 2. Because the integral from 0 to pi over 2 is this part on the right. And so if we wanted to go from negative pi over 2 to pi over 2, then we just have to double it, because you get the same area on both sides. All right, so we call this type of function an even function, because something like x squared or x to the 4th or x to the 6th, right, x raised to an even power is going to have this property where it's symmetric across the y-axis. So we call these even functions. And if we said g of x is an even function, so an even function is one where g of negative x is equal to g of positive x for all x, in other words, g is symmetric across the y-axis, then if you want to take the integral between negative a to a, well, from negative a to a, it's like having 2 copies of the area between 0 and a. Right, you get the same area on either side, so you get 2 copies of the area from 0 to a of g of x. This should have a dx. Okay, so why is this useful? I don't know, sometimes it's easier to do a computation from 0 to a than it is from negative a to a. But honestly, this is a more useful one up here, because if you know that the function is odd from the get-go, you don't have to do the work of finding the antiderivative and then evaluating it at the endpoints. If it's odd, you can just say, well, it's symmetric on either side. There's going to be positive area on one side and negative area on the other side that will cancel each other out, and you just get a nice derivative of 0. Okay, so that's sort of a neat property of integrals for symmetric functions.